So this question, we've got a roller coaster, and the question is basically going to be, from what height h here, can the roller coaster be released such that it successfully travels around that loop here without falling off anywhere in this loop or at here, basically. Okay, the roller coaster in this question is shown here. Let's move on to the first part. Okay, so in the first part, we need to find the velocity of the trail at point A. This is just a simple question about conservation of energy. So the initial energy is mg big H, and that must be equal to half mv squared at A. So V is equal to the square root of 2gh. Therefore, the answer is D. Move on to the next part. Okay, now in this part of the question, we're told that the roller coaster follows a circular path and reaches the top of V. We need to find the velocity there. So now we're going to use conservation of energy, but we need to think more carefully about the change in height. So this height here is going to be diameter, so this is going to be 2r. Therefore, the change in height is only h minus 2r. Therefore, the change in gravitational potential energy is just mg times that. And this must be equal to the kinetic energy of mv squared. Therefore, v equals to the square root of 2 g and h minus 2r. Okay, so we have the expression for v now, so therefore the answer is E. Let's now move on to the next part. Now, we're talking about centripetal acceleration here, AC, of an object moving in a circular path of radius r at speed v. We're given this formula here. We need to state which direction this acceleration acts. So let's think about this. We've got a circle, and since the velocity of the object moving in a circle is changing, then we can see that there must be an acceleration on the object. So if the speed v is constant during the motion, then we can see that there is no component of acceleration that's parallel to the path of the circle. Therefore, we conclude that the only direction of acceleration must always be towards the center of the circle. Because if it was not towards the center of the circle, i.e. in any other direction, then the object will tend to move away or in some direction that's not towards the circle. Now, in this case, in particular, you can analyze this further and see that the velocity and the acceleration are perpendicular. Therefore, the acceleration is not causing the object here to move closer to this point here. So that's why the acceleration must be towards the center. So therefore, the answer is B. Okay, so now in this part, we're considering the forces when it's at B. So let's bring back the diagram. So this is the diagram now. So we're talking about this point B here, this point B, and we say that it cannot lose contact at B. So recall from the last part that the velocity at B was given by the square root of 2g times h minus 2r. Okay, so we know the velocity at B, what it is. Now, what is the condition on B? Let's examine the forces at B. So if the object here, there's going to be the weight mg, and there is also going to be the normal reaction here. So from this, we can see that the resultant force towards the center of the circle is the normal reaction plus the weight. And we know that this must be equal to the centripetal force from the previous part. So that must be equal to m times the velocity squared divided by the radius of the circle. And therefore, we know that the normal reaction is just mv squared over r minus mg. Now, since it does not lose contact, we need that this to be strictly greater than 0. Substituting in our result for v, we get that 2g h minus 2r divided by r minus mg, sorry, I missed an m here, is greater than 0. So I divide through by m, divide through by g also, and I get h minus 2r must be greater than or equal, 2 times this must be greater than or equal to r. So let's expand. This gives us 2h minus 4r is greater than r, and this gives us h must be greater than 5r over 2. So answer is D.